Is it audible? ठीक है. Good morning, good afternoon, all the participants, and welcome to the 5 days online workshop on emerging CMOS technologies and beyond, trends and challenges. This workshop is for 5 days from 26 November to 30th November 2020. I also welcome Professor Vijay Janyani, Head of the Department, Electronics and Communication Engineering, and also welcome Dr. Rohit Bhakar, TechCube Coordinator, MNIT Jaipur. So I'll give brief idea about the event that is going to conduct for 5 days. The aim of the workshop is to will provide an opportunity to learn the recent trends and challenges in the area of CMOS technologies and its beyond from eminent expert from IITs and NITs. So we have today's expert, Professor Brajesh Kumar Kaushik from IIT Roorkee. So he will be delivering the first talk from 3 p.m. onwards today. The participation will get an exposure to the state of the art in CMOS IC design, layout design, SPICE modeling, and challenges in advanced semiconductor devices for various applications. This workshop will provide discussion presentation on future research direction in the field of CMOS technologies and beyond. The participant will also learn a new simulation tools, EDA and TCAD tools from academic and industry expert. The topics to be covered, we have already mentioned in the details in the brochure. Okay. So first the schedule of the event is like that. We have the talk of today's from 3 p.m. onwards by Brajesh Kumar Kaushik on Spintronics perspective and challenges. After that, we have a introduction to TCAD tool today scheduled from 4 to 5 p.m. And after the second day of the workshop, we discuss about the various short channel effect coming from the CMOS scaling and method of logical effort design. And after that, the second half, it will be cover the CMOS logic design and its challenges and SPICE modeling. So how to design a SPICE model and how it can be utilized for the circuit simulation will be discussed on the second day. Third day, we have focus on the layout design part especially and demonstration of the cadence tool, how to design a good layout for CMOS integrated circuits and what are the upcoming challenges in the layout design. And then after that, SPICE modeling will be covered, the advanced topics, advanced analysis like Monte Carlo simulations, all those things will be covered in the third day. Fourth day, we have the structural design in terms of TCAD simulations. And TCAD simulations, we discuss about the advanced topic like how to design a tunnel FET using TCAD tool for biosensing application, light sensor application, and energy harvesting applications. And then we have an expert from the Intel analog design engineer, Dr. Sunil Pandey. He will be discussing about especially the using advanced CMOS devices. We have a few discussions on the doping technology, RF and analog performance of the different FinFET architecture that will be discussed in later on the stages at the last day of the workshop. So in this workshop, we have around 125 registered participants. Out of that, 25 participants are faculty members and 100 participants are from different background. They are PhD scholar, MTech, like 11 MTech scholars have joined this event, and there are two more from the NIT Durgapur, NIT Nagpur, and few from the as well. So I once again welcome all the participants for this workshop. Hope we'll enjoy the session in the future. Okay. Now I request Dr. Rohit for introducing about TQ, because this workshop is organizing support of technical quality education improvement program of cell of MNIT Jaipur. Without their support, will not be able to organize such kind of event. And Dr. Rohit was organizing this kind of event. And yes, yes. Hello, sir.
Hello.
Over to you, sir.
Am I audible?
Yeah.
Thank you, Dr. Chitrikant. Respected Vijay sir, Head of Department Electronics and Communication, MNIT Jaipur. The organizers of this event, Dr. Chitrikant, Dr. Bharat, and Dr. Rajesh, and all the participants who are attending this ICT Academy course, ICT Academy, as well as MNIT. I think it is a welcome step that they are organizing a 5 days online workshop on emerging CMOS technologies. We have been receiving, as TechUp coordinator, we have been receiving a large number of requests from students at the undergrad and at the postgrad level to have courses which reflect the teaching that is to be done at the undergrad as well as postgraduate level. And I feel, I'm looking at the content, it is an apt course which defines the new technologies that are emerging in this segment and how they can be made relevant to the present industry structure. As such, MNIT Jaipur, TechUp, and electronics department as a whole, they have taken a lot of initiatives. Despite the restrictions of Corona, they have done a large number of courses which are relevant to the students and their placement for the industry. And this is one of the courses in that series. And I'm sure, looking at the large number of participants who are attending, they would be attracted and would benefit from the interactions that happen. We have good speakers from IIT Roorkee, from a large number of them from NIT Jaipur and other NITs. I'm sure that the level of discussions that would happen during this course would benefit all the participants who are attending this course. And as SECIP, we continue to contribute towards the growth of the technical education in this segment. So good learning and happy times while you are attending this course. Thank you, Dr. Chitrikant, for inviting me for the inaugural session. Thanks a lot. Thank you very
much. Thank you very much, sir, for your kind words and always encouraging us to organize such kind of events. Now I request Professor Vijay Janyani, Head of the Department of Electronics and Communication Engineering, for a few words. Sir, is it audible, sir? I think so. Vijay sir, are you there, sir?
Yeah, I'm there. Am I audible?
Yes, sir. Audible, sir.
Yeah, okay. Yeah, so I welcome all the participants here who are present in this 5-day online workshop on emerging CMOS technologies and beyond, trends and challenges. So I extend a very hearty welcome to you on behalf of MNIT Jaipur, on behalf of Department of Electronics and Communication Engineering, and also on my personal behalf. I also congratulate Dr. Chitrakant, convener of this course, and Dr. Bharat Chaudhary and Dr. Rajesh, who are the coordinators of this course. The CMOS technology, as you know, it is a very emerging technology, and a lot of research is it has already been done, and already a lot of achievements have been made, and still we need to make more achievements because the size of the devices is shrinking day by day. So we need to keep the power consumption and the speed also under control. A lot of new applications like 5G and smart cities, all these are actually percolating our daily lives. So we need very high speed switching to support these applications. And of course, CMOS is going to play a very major role in this. Without CMOS, we cannot imagine our electronic world or digital world. There would be no PCs, no TVs, or no cell phones, no GPS, no printers, nothing. So obviously, this CMOS technology is a very current and very important technology. And as Dr. Chitrakant has already mentioned, this workshop will provide an opportunity to learn recent research and development in this area, and you will also get a experience of the tools, various simulation and analysis tools, EDA and TCAD tools, which are available in this domain. So I would like to take this opportunity to introduce briefly the Department of ECE to the audience. This course in electronics and communication engineering, it started in 1984. Initially, it was within the electrical engineering department, but soon, 1994, it became a separate department. And since then, it has been one of the most popular and sought after department by the aspirants who are aspiring to come into engineering from all over India. And it enjoys a very good reputation among all the NITs and IITs. And also within MNIT, this is one of the largest departments of the institute. Currently, this department offers one UG program, and we have 4 PG programs. That is Electronics and Communication Engineering, VLSI Design, Wireless and Optical Communication, and Embedded Systems. So these are 4 major research areas of the department, which I think it covers every diverse field of today's whatever developments are taking place in this field, broad area. And apart from these 4 MTech programs, the department also offers PhD programs in all relevant areas. And the department has received numerous grants and projects from various government and semi-government and industries also, that include DRDO, MHRD, UKRI, DST, and ISRO, and many other agencies. And as far as the faculty members are concerned, we have a very good strength of faculty, both in terms of numbers and both in terms of quality also. We have around more than 25 faculty members in the department working in different diverse areas within this broad field. And I would like to say that we have a mix of, a rare mix of very experienced faculty and very dynamic faculty, young faculty also. So that is about the department. And recently, department has also received a grant of 1 crore 25 lakhs from Government of India under the FAST program, 2019. So, I mean, given all these facts, I would again welcome all of you to this 5-day course. And I once again congratulate the organizers of this program, Dr. Chitrakant, Dr. Bharat, and Dr. Rajesh, for making efforts and for arranging and requesting very well-known experts who will be giving talk in this course. They are from IITs and NITs. So I am sure that with the efforts of the coordinators and conveners and with the knowledge being imparted by the experts, this will be a very useful learning experience to all of you, and you will definitely, I hope, will take away some new ideas for your research and teaching in this area. So thank you very much. Dr. Chitrakant, can you hear me?
Yes, sir, you are audible. I think there is a network connection lost at the office. Yeah.
Okay, I see. Yeah, Chitrakant, I have finished. Your voice is not audible, Chitrakant.
Is it audible, sir, now?
Yeah, now it is audible.
Hello?
It is audible now. Yeah, it is
Okay.
audible.
Thank you very much, sir, for variable feedback and encouraging us regarding the workshop. And definitely we'll organize such kind of event in near future also. There is one and directors are about to join, but because of some work, he is not able to join in the inaugural ceremony of this workshop. So we thank director sir also for giving us constant support to organize such kind of activity through TechQ and other fundings. Now I request Dr. Rajesh Shah to say word.
Hello, good afternoon everyone. I, Dr. Rajesh Shah, coordinator of this workshop, on behalf of organizing committee, would like to thank our chief guest, Professor Uday Kumar Yaragatti, Director MNIT Jaipur, for accepting our invitation and for his inspiring mentorship and the encouragement. I am also sincerely thankful to Professor Vijay Jandani, Head Department of Electronics and Communication Engineering, Jaipur, for his continuous support and useful suggestion, which have greatly helped to our successful hosting this workshop. I convey my gratitude to Bhakkar, Technical Coordinator MNIT Jaipur, for accepting our invitation and blessing the inaugural session. I take Dr. of this workshop for his precious support and help. And in this workshop, we have participants from various NIT, IIT, IIT, and reputed university, and as well as the institute also, including faculty, PG, PhD, and UG students. And I welcome all the participants to this 5 days workshop on CMOS technology and trends. I hope you all will be benefited from this workshop, and it shall be helpful to assist further to carry out some research in the area of CMOS technology. Thank you all, and welcome all the participants to this 5 days online workshop on CMOS technology. Thank you.
Thank you very much, sir. The inaugural session come to the end. Now I request we'll move forward to start with the first session of this workshop. So now I request Dr. Bharat to introduce our speaker. I think our speaker is already joined the session. He's online.
Good afternoon, all the participants. So before inviting to our inaugural speaker, I want to introduce our speaker first, Professor Brijesh Kumar Kaushik from IIT Roorkee. Dr. Kaushik received her Doctor of Philosophy in 2007 from IIT Roorkee, India, and he joined Department of Electronics Communication Engineering, IIT Roorkee, as Assistant Professor in December 2009. And since April 2014, he has been an associate professor. He has served journal chair, technical chair, and keynote speaker of many reputed journals and national conferences. Dr. Kaushik is a senior member of IEEE and a member of many expert committees constituted by government and non-government organizations. His name has been listed in Marquis Who's Who in Science and Who's Who in the world. So Dr. Kaushik has been confirmed for award of IEEE Electronic Device Society EDS to offer EDS chapter website with Kali lectures in his research domain. He has published 12 number of books to his credit by reputed publishers such as CRC Press, Springer, Artec, and Elsevier. His research interests are in the area of high-speed interconnects, low-power VLSI design, memory design, carbon nanotubes design, organic electronics, FinFET device, circuit code design, electronic design automation, Spintronics-based devices, circuits and computing, image processing, and optics and photonics-based devices. So this is all about that introduction part of our inaugural speaker. Now I invite Professor Brijesh Kaushik for delivering the speech for the session.
So, Professor Brajesh, sir, over to you, sir. Salis, can you make him a presenter?
Yeah, can I share my slides? So my slides are shared or not?
Not, he's already presented.
Yeah, so I have shared my slides. Can you see my slides now?
Yes, Professor Brajesh, they are visible. You need to, I think, go to the slideshow mode.
Yeah, I'll do that.
It's visible now, better.
Right, perfectly okay now. So thank you very much to all of you for inviting me to deliver this talk in this faculty development program. I believe that most of the candidates would be coming from different backgrounds in electronics, electrical, and computer science. I'll be actually taking you to a completely a new topic related to Spintronics. And in fact, what I understand is that most of the people might be having some understanding about electronics as well. So my topic actually would be more oriented towards memories, which have actually made Spintronics really very enticing for the whole microelectronics and nanoelectronics community. So I'll start off with some of the introduction related to the new memory technology, why they are required, and how we have moved during last, I would say, a century, when there had been a lot of developments related to memories. I'll be taking you through those things. And then we'll try to see how Spintronics has really come up in last 1 decade or so. So once we are done with those things, we'll go into the fundamentals of Spintronics, how actually the memories are operating in Spintronics domain, those kind of things we'll be looking into. Then we'll be moving on to some of the basic devices which are used for storing the information in all these Spintronics based devices, such as your magnetic tunnel junction, your spin transfer torque MRAMs will be going into spin orbit torque MRAMs, your domain wall, racetrack memory, and then we'll be moving on to some of the design aspects which are quite important when we work out with these spin-based memories. And in the interest of some of the candidates or some of the faculty who want to shape up their career in the area of Spintronics, we'll be looking into the simulation aspects also of these STT-MRAMs. And then we'll wind up the things with certain future perspectives which are there still available in Spintronics or maybe some other domain also. So let me start with the introduction, how memories have evolved over the time. So this slide actually shows you the picture how things started off from more than a decade or maybe a century ago. So wherein you can see in 1800 or 1900s how the things were actually working out. So there actually we had a requirement of memories, and that was fulfilled by these punch cards wherein we used to store some of the information. Then in 1920s we went on with magnetic tapes, and in 1930s we had this magnetic drum, mechanical memory where we could store information onto them. And then after a decade, when the tube era actually came up, we had memory again implemented using these Williams tubes, electron tube, delay line tube. So all those tubes were used for storing the information. And then with the development of ferrite cores, we were able to come up with some hard disk also, right? So that was the era in 1950s. And then 1960s, I believe most of you would have seen the music tapes, the cassettes that we used to have, and wherein we used to have different songs recorded onto it. And these songs were actually placed on the both sides. I mean, whenever you play the cassette on the one side, maybe from left to right or right to left, you had different set of information stored onto it. So that was one way by which actually we could store a huge amount of information onto these music tapes. But then these music tapes were not that reliable. Maybe after 100 or 200 runs, we actually were not able to retrieve the whole information exactly. There was some randomness that was generated, the noise and other things. And then during 1960s itself, there was an era when DRAM was actually introduced. And then 1970s, we had some good bubble memories or hard disks, which actually evolved very nicely. And then in 1980s, I believe most of us would have seen CDs, and some of us would have seen floppy disk also. Now, if you try to recall, these floppy disks were really very unreliable. In fact, if I was supposed to deliver some talk at some place, I myself used to carry 2 or 3 sets of floppy disks. And these all floppy disks were so unreliable. Probably I would have actually not, I couldn't not use all of them, maybe for one reason or another reason. And there were cases where all 3 floppy disks could not work because of some of the compatibility issues or some unreliability or some other issues. So they were not quite reliable to be used. And then came the era of CDs. So at that point of time, CDs were considered to be really a jump forward where we could store something like 700 MB of information in comparison to something like 1 or 2 MB just on these floppy disks. So it was almost 700 times increase in the information storage. Thereafter, in 1990s, we had these DVDs, which were even prominent for having more data stored onto it. So I can recall that in the CDs, I was able to store only half of the movie, half of the Hindi movies that were popular at that point of time. But then with DVDs, I could actually store something like 3 or 4 movies on a single DVD. So the amount of information, I mean to say, could be large enough to be stored in these DVDs. But as on date, with many drives and other flash drives and other kind of memories, I think DVDs have also been outdated. So they are all obsolete as on date. I think most of our laptops or desktops, or even our audio system in our car do not carry these kind of drives. So that is how actually things have unfolded in last several years. You can see that every decade there has been a complete change in technology. And from 2000 onwards, there are many other kind of memories which are coming up. So you have memory stores, STT-MRAM, ferroelectric RAM, phase change RAM, resistive RAMs, all kind of memories are coming up. And all these memories, if you see, they have huge capacity to store. And of course, we are always trying to make them as fast as possible. Now, the next slide actually shows you very clearly about the memory hierarchy. So most of the computer scientists or electronics engineers do actually work out with all these memories when designing any system. So maybe you have to use non-volatile storages also. Of course, you have to depend a lot on main memories such as DRAMs. Then you have your SRAMs, and then within SRAMs you have different levels of caches depending on how fast they are and how reliable they are. And as you move up, you have your register files, ALUs, flip-flops, so on and so forth. Now, this memory hierarchy is quite interesting to see in terms of the capacity that you have, the cost per bit of all of these memories, and the speed by which you can access those memories. So if you see in this hierarchy on the bottom, you have this non-volatile storage, which can store something like information in terms of something like terabytes. Now, the biggest challenge with these kind of memories are that they are very slow. The speed is something like 1 millisecond for accessing each bit of information. So by any means, in this era, this 1 millisecond is quite big time. Now, one of the good things about this non-volatile storage is that they have very huge capacity. So if you want to store the data for a long time without putting up too much of power dissipation onto it, you can of course use these non-volatile storages. So I think most of you might be using some portable hard disks, and these portable hard disks do depend a lot on these kind of non-volatile storages. And the cost, if you see, for storing 4 terabyte or 5 terabyte of information is just $5,000. Whereas if you try to compare with a RAM, with a SRAM, especially the level 1 or level 2 caches, wherein you put something like 10 GB of RAM onto any system, probably that would be costing you a huge amount of money. So a mobile phone that you might be carrying, if you have 10 GB RAM onto it, the cost would suddenly go up by many, many thousands. So if I try to see any mobile phone of some branded company having 10 GB of RAM, that would be costing me something around 50,000 to 60,000 bucks. Right? So the reason behind that is you want to have memories very close to the processors, which can actually operate at very high speed, and that decides the overall performance of your chip as well. Other than this, your SRAMs, if you see between your SRAM level 3 and level 2 caches and your non-volatile storages, there is a main memory. And you call it as main memory because most of the storages that you do goes to these DRAMs. But then the problem with this DRAM is that the access time is quite slow in comparison to SRAMs, but it's quite faster than your non-volatile storages. And it lies somewhere in between as far as the capacity is concerned, as far as the cost per bit is concerned. So that is how you actually call it as main memory. But the biggest bottleneck with all these DRAMs is that with bigger and bigger DRAMs coming in at your data center applications, these DRAMs itself consume a lot of power. Now, of course, you do consume a lot of power with SRAMs also, right, in terms of leakages that you have. But there are certain things that you have to balance when you are coming up with any system. So while designing any system, you have to take into consideration all these kind of memories. You have to see that which memory will fit into what kind of applications. And also you decide how much memory you are going to use for that purposes. So this is how the memory hierarchy looks. Now, the biggest challenge, as I mentioned, with all these memory technologies beyond 45 nanometer technology node, you have huge amount of power dissipation, and that has to be taken care of. So there have been a lot of studies conducted by different nations, and as far as Japan is concerned, there are people who have done a lot of analysis over that, and they say that in fact, if the internet proximity and internet access by all the people across the Japan do have to go through this internet, probably the data centers where you have to store the information also for putting up all these internet usages and data. Probably the data center power dissipation will go up in comparison to what is being generated in Japan in a decade or so. So you can understand how much power dissipation these data centers are taking up. Probably they will match up with the power generation capacity of any nation if things are not taken care of. So the power dissipation sector has to be looked into very aggressively. And as on date, if you talk about people who are using Gmail or some other kind of email system, and each of them have something like 15 GB of data available with them, and all of them start using to their maximum possible extent, the data centers where all the information is stored is going to take up huge power to keep that data alive itself. So that way, it's very important that the memories that we are using, either in form of flash or DRAM or SRAM, the power dissipation has to be reduced as much as possible. Now, within the system also, you see that SRAM, with each technology node, the power dissipation is increasing, especially the leakages are increasing 10 times with each technology node. So that way, SRAMs are also taking up too much of power. Now, when you talk about DRAM, it inherently takes huge refresh current to keep the data alive. And that way, you keep on paying the price in terms of power. Whereas when you talk about flash memories, which often keeps your BIOS intact in any of the systems, right? So they are also marred by different kind of high power dissipation or slow write speed. Now, often when you are talking about BIOS, probably you don't have to write many number of times. But when you talk in terms of keeping the data for large number of cycles, where you have to write and erase, write and erase, probably the endurance issues do come up very rigorously. So those endurance issues have to be taken care of. And apart from this, as I mentioned, the power consumption in portable and data center applications has become a real issue as on date. And in any of the memory systems, the key performance block is something like power dissipation, and therefore the memory blocks have to be designed properly. Now, I think you'll be going through different talks in this FTP also, and at different other places also. Silicon already has come to a place where you have to find out an alternative to the silicon-based transistors as well. Probably either we have to change the structures or we have to change the materials. So those are the two ways by which you can make it work. Otherwise, things won't be in a good shape, maybe in next decade or so. So we have already moved on from planar transistor to your FinFETs, GAA, and also now nanosheets are being considered aggressively. But then once nanosheet, probably we can reach up to 3 nanometer. But then after 3 nanometer, it's really very difficult to replace it by other structures. And then we do consider that silicon would be towards the end of technology roadmap. But here, actually, we are not much bothered about the transistors that are being used for driving different memories. But the important issue that we are going to take up in this talk is related to how we are going to store the information using different technologies, especially your Spintronics based technology. Now, the next slide actually again shows the issues with different nanoscale devices, especially in terms of designing them with low voltage, targeting low power, and that too taking up them with energy efficient circuits also, and maybe scaling them up onto certain systems. Now, taking all these things into consideration, if you see the problems with their present memory technologies are that you have high static leakage power with your SRAMs especially. When you talk about SRAMs, again, the large footprint area is something which is of big concern. I think the candidates who are present in this FDP might be knowing that SRAM requires minimum of 6 transistors for storing 1 bit of information, whereas the DRAM can store the same information using just 1 transistor and 1 capacitor. So that way, the silicon area taken up by DRAM is quite small in comparison to your SRAMs. But then this SRAM actually has a lot of high static power dissipation, and the size itself, the silicon footprint area is itself quite big. Now, if you try to see that these memories, if you just categorize them into 2 types, one is your on-chip memory, and the other one can be your off-chip memory. Now, when you talk about on-chip memories, most of them are volatile. They are having low density, and therefore the cost is quite high, especially the SRAMs. Now, each of these memories, actually, if you try to see any processor or any chip as on date, most of the footprint area is occupied by the memories only. So it is almost 50% of the chip area that is occupied by these memories. Now, when you go to off-chip kind of memories, most of them are non-volatile. They are, of course, coming up with high density. And the biggest problem with them is that they have very high access time. So if you see, the access time is quite high. And that is where we are quite bothered about non-volatile memories. Now, when you talk about all these memories, when you're designing with your CMOS, maybe SRAMs or DRAMs, they're highly dependent on scaling also. So if you scale it maybe from one technology node to another technology node, your whole design sometimes have to be changed completely. So therefore, all these designs, performance, and other things do depend a lot on CMOS scaling as well. Especially, I'm talking about maybe a reliable SRAM where we have something like 10 transistors or 11 transistors or 9 transistors. So the performance itself changes if you go from one technology node to the other technology node. So keeping all these things in mind, and knowing that all of them have been put into different blocks, your emerging non-volatile memories have to be looked into. There have been a lot of research which has been conducted across the world of finding the suitability of non-volatile memories for different technologies. So we would like to have a memory that can fit into any of the blocks, the memory hierarchy that I have been showing. So we'd like to have a memory that can work as good as your DRAMs. So all the good properties of DRAM should be there. All the good properties of your SRAM should be there. And also all the good properties of non-volatile storage should be there. This is what we expect. Now the new universal memories, that is why we call it as universal, because it has all these good properties in terms of high density, similar to what we have with your DRAMs or your non-volatile memories. It should have smallest footprint area. That is what we have with your non-volatile memories or your DRAMs. It should be non-volatile, reason being that you do not consume any power, even if you're not changing the information. So that is what actually you would require from non-volatility. Apart from this, it should have least excess time. It should have unlimited endurance. I mean, you can write down endlessly and you can read out of it endlessly. So you can keep on writing onto it every cycle, and maybe as far as silicon is concerned, you can write it down 10 raised to 16 times. So that is what the lifetime which we call. Of course, it should have minimum leakage power. All these kind of universal memories, that is what we have with your non-volatile memories also. So if you keep it intact for a very long time, you don't have any leakages through it. Whatever you have stored today maybe would be available after many years also. Other than this, whatever technology that we develop, that should be process compatible. So if we have developed something like spin-based memories, they should be fabricated on the current fabrication lineup itself. You don't have to think about coming up with a completely new process. So that should be compatible, right? So whatever memory that you're introducing. And this is one of the reasons why many of the graphene-based transistors, many of the other material-based transistors or technology has not come up very rapidly. Reason being, they are not compatible with current technology nodes, or I would say the current fab lineup. Now, taking all these things into consideration and the properties that you would like to have with this universal memory technology, we would like to see actually what kind of technologies are really available as of date that can be fitted into all these kind of properties, the best of all. So if you see the emerging non-volatile memories, you have different technologies such as your spin transfer torque MRAMs that we are going to discuss today, the racetrack and the domain wall memories, which are also a type of spin-based memories. Other than this, you have this ferroelectric RAMs, your phase change RAM, and your resistive RAMs. So if you talk about phase change RAM especially, so these phase change RAM actually changes the material characteristics as you move on from one data to another data. So I think most of you from your class 12th days can recall that your material had two kind of states. One is your amorphous state and the other one is your crystalline state. So most of these memories, which are most of the material, if you see, when they are in amorphous state, they are highly resistive. Whereas the memories or the material which are in crystalline state, they are highly ordered. And once they are highly ordered, that means the resistance is also quite low. So what happens is, as you move on from amorphous state to a crystalline state or crystalline to amorphous state, what you do is you keep on changing the resistance level. And that is where you actually find out what has been stored. So either you will be in amorphous state or you will be in your crystalline state. And accordingly, you can easily identify what is the state of that material, whether it is in high resistance state or low resistance state. And based on which, you can identify whether 0 or 1 has been stored onto it. That is how your phase change memory works. So now the question is, how would I change the state from amorphous to crystalline or crystalline to amorphous? And that can be done easily by some heating element available. So that heating element is going to heat up a very small portion of that material to change the state from amorphous to silica to your crystalline or crystalline to amorphous. And that heating is done by some small amount of current that would flow through a filament. That current can be something around nanoamperes or even lesser than that. But of course, they're going to take some toll on power dissipation, overall power dissipation. And then resistive RAMs. Resistive RAMs have been there for a very long time. So that is also going to work out on the same principles where you change the resistance. So that resistance change can happen because of some filament reaction that happens between the two terminals. And between those two terminals, you are going to again take up some material which has two different states of resistance, either because of creation of some filament or not because of any filament. So resistive RAM has been there for some time. And of course, these resistive RAMs have some component of unreliability also. So I would like to have all these kind of emerging non-volatile memories compared. So we'd like to compare them also in the next slide. So this is where you see the comparison of all emerging memory technologies. And when you see this comparison, I have done it into two portions. One is your volatile ones and the other one is your non-volatile. So this volatile ones contains all these SRAMs and DRAMs, which are already there. So DRAMs has been there from last 50 years. So this year, Intel has been celebrating the inception of DRAM, and that is what they're doing for this 50th year. Now, SRAM also has been there for quite a long time now. And as I mentioned, this SRAM actually is going to store 1 bit of information using 6 transistors. DRAM can store that 1 bit of information using 1 transistor and 1 capacitor. And then you have some other non-volatile storages. So these non-volatile storages, which I have put forward in front of you, is your NAND flash, which is an existing technology, which is currently being used in your mobile phones and many other places. Then you have your ferroelectric RAM. Then you have your phase change memories and your STT-MRAMs. And what we are trying to do in this slide is we are trying to compare it based on some of the prominent performance parameters, such as data retention, cell area, read access time, then your write or erase time, rewrite endurance, the standby power that you have, then your read or write power, supply voltage up to which it can work, and whether that product is available or not. So if you try to see data retention, your SRAM and DRAM fails miserably in this case. Reason being that as soon as you switch off the power, the data retention would not be there. The whole data would be lost once you switch off the power. Whereas the non-volatile ones on the right side, they will of course retain the data even if you switch off the power. Now, when you talk in terms of cell area, as I mentioned, that SRAM is going to take large area for storing 1 bit of information. So similarly, you can see over here that the cell area for your SRAM lies between 80 to 120 F square. So F is your feature size of the transistors that you're coming up with, the minimum dimensions that you will come up with in the fab. So the cell area of this SRAM is something like 80 to 120 F square. Whereas when you go to DRAMs, the size is something like 6 to 12 F square, which is pretty small in comparison to your SRAM. Reason being lesser number of transistors. Now, as you move on to non-volatile storages, NAND flash is pretty small. Ferritic RAM is fine. Your PCM is also quite small. And then when you see STT-MRAM, it is also pretty small in comparison to what you see with your ferritic RAM, PCM, or your SRAMs. So the cell area of this STT-MRAM is almost overlapping with that of your DRAM, which is currently considered to be a very small memory dimension. When you talk about read access time, your SRAM is something which is considered to be the fastest one. Still, it is fastest. But then if you see your STT-MRAM, it again overlaps on the lower side of your SRAM. Quite fast. Whereas your FERAM is quite slow, 20 to 80 nanoseconds. And your NAND flash is also quite slow. When you talk about write or erase time, the situation is worse for your NAND flash, which takes 10 to the power 5 to 10 to the power 7 nanoseconds. So that is where actually you cannot use this NAND flash for different purposes in your chip. So what we are trying to do over here is we're trying to find out the best alternative to SRAMs or DRAMs. When you go to read-write endurance, your SRAMs and DRAMs have the highest one. And when you talk about NAND flash, the situation is really not good at all. And when you compare it with ferritic RAM or PCM, the situation is somewhere quite low, 3 orders lesser than what you have with your STT-MRAMs. So especially if you see STT-MRAMs, that is really matching up to that of your SRAMs and DRAMs, much better than what you have with other kind of memories. When you talk about standby power, your SRAMs have huge power dissipation even if you are not changing the data, even if you're not using it at all. If you keep it intact, still there's a lot of leakage current that flows through these SRAMs. And that is why these SRAMs are considered to be quite slow. Quite dissipative in terms of power. DRAM inherently has to refresh all those charges that are stored in your capacitor. So since these capacitors are leaky inherently, they're always going to refresh those charges. You're going to replenish those charges so that the data is kept intact. So keeping all these things in mind, what you find out is that your NAND flash, as far as standby power and other things are concerned, you don't have to worry much in all these non-volatile memories. When you talk in terms of read or write power, the situation is something like similar for your SRAM, DRAMs, and your FERAMs, PCM, and STT-MRAM. Whereas when you talk about NAND flash, the read or write power is quite high, and that is what renders it for its usage in on-chip VLSI memories. Now, when you talk about supply voltages, your SRAMs can, of course, work at even sub-threshold voltages. That can go up to 0.3 or 0.2 volt also. Whereas DRAMs and other kind of memories have to operate at comparatively higher voltages. If you try to see NAND flash, the operating voltage is quite high. Whereas your STT-MRAM can, of course, work below 1.5 volt also. So this can be even much more lower if you are able to redesign things in a proper way. As far as product availability is concerned, all of them are there for a long time. And PCM has also come up, but still being looked after whether it is commercially viable or not. So this is how you compare all performance parameters of volatile and non-volatile memories. And when you see all these comparisons, what strikes your mind is that your STT-MRAM is going to work out really well in comparison to any of these memories that you have. And once you're convinced that STT-MRAM is going to work out well, it's very important that we need to understand the operating mechanism of these Spintronics-based memories. And before going into these Spintronics-based memories, it's important to understand actually the working of these STT-MRAMs as far as Spintronics technology is concerned. So we'll just have a look onto the fundamentals of Spintronics over here, where we try to see the comparison of electronics and Spintronics. So I believe most of you have already gone through some of the electronics while designing your MOSFETs, while designing your planar ones or GA or some other kind of memories. As far as Spintronics is concerned, you can see that the state variable is spin of electron. Whereas in electronics, the state variable is all charge of electron. When you see the properties that you have to follow in electronics are all classical ones. Whereas in Spintronics, you have to do a huge amount of quantum mechanical effects. You have to take all those things into consideration, and therefore it's quite pertinent that you have to look into all these properties properly before you understand all these Spintronics-based materials. When you go into the materials, the electronics is solely dependent on your conductors and semiconductors, whereas your Spintronics is quite dependent on quite different set of materials such as ferromagnetic material or non-magnetic materials. Now, when it comes to performance, your electronics has limited speed and high power dissipation, whereas when you talk about Spintronics, they have quite higher speed and also they consume very less power. That is what you see in this case. You have upspin and downspin, left spin or right spin that actually generates all these kind of magnetic field. Now, the basic attributes of spin, as I mentioned, are electron spins that originates from the origin and in fact from the intrinsic angular momentum. The two spin states, as I mentioned, are spin up and spin down. And in magnetic field, your electrons, the important thing about it is that in magnetic field, the electrons which spin up and spin down have two energy states also. So they have two different energies, and by which you can clearly identify whether 1 or 0 has been stored in that kind of material. So now moving forward, different mechanisms that goes on in your Spintronics material, such as your spin injection and accumulation, spin detection, and spin relaxation. What you see over here is the non-magnetic material that has equal number of downspin electrons and upspin electrons. And so once they are balanced, that is why it is called non-magnetic, the density of states on both sides seems to be equal. Whereas for ferromagnetic material, the upspin and downspin states are quite disbalanced. And that is why you see a net magnetism in that material, let it be a small or large. Now, how to inject the spin onto a non-magnetic material and how the energies will change. So this shows you a very good mechanism of ferromagnetic material which has a magnetic moment in the upside and a non-magnetic material placed beside this. So if you apply some current onto it, what will happen? The magnetic moment or the electrons which are having an orientation of upside would be injected onto the other side also in this non-magnetic material. And this goes down as you move away from the center spot or the junction. So this is how you are going to inject spins into the non-magnetic material. And this has been shown here also. You have with I is equal to 0, no current flowing through it. The non-magnetic material remains as it is, does not make any change. Whereas if you apply some current which is greater than 0, what you are doing is you're injecting a particular spin into the other side. And that is where you see a difference in the state. The spin detection, actually that spin detection can be done based on some of the fundamental equations such as LLGS, Landau, Lifts, Gilbert, Solansky equation that relates your magnetic moment with your precision torque, damping torque, and your spin torque. That is how it has been related here. And what you see is the spin torque is balanced with that of your damping torque. If it is balanced, you'll see some precision of these electrons going across. So if the spin torque that you apply is large enough, the orientation of the spins can actually reverse also. That is what you see over here. If the spin torque is large, it may reverse its side also. And that is how you switch the MTJs. So this slide actually shows you the giant magnetoresistance of a spin valve, which is quite interesting structure. And this is where actually the foundation for Spintronics memories were laid down. Now what you see in this case is you have a three-layered structure wherein ferromagnetic material is at the bottom, you have non-magnetic spacer in between, and a ferromagnetic material on the other side. This ferromagnetic material can have orientation either in this direction or in this direction. The two directions are possible, and based on this, you have a state, a comprehensive state of either parallel, wherein the ferromagnetic at the top is having an orientation which is parallel to what you see with the fixed layer, right? So this is a parallel orientation, and this is the second case when it has orientation in opposite direction, and that way the free layer and the fixed layer are acting anti-parallel to each other. So this is your anti-parallel state, and this is your parallel state. And if an electron has to go from one side to another side, and if it is oriented in this direction, it won't face any scattering. It won't face any collision or scattering. It will straight away go from one side to another side. Whereas in this case, irrespective of whether it is having the orientation similar to what you have with a fixed layer or opposite to that, it will have some scatterings on the both sides. And that way, the resistance of your anti-parallel would be higher in comparison to your parallel state. And these two resistances are actually is going to let you know whether 1 or 0 has been stored onto this GMR. So the crux is that these two states, either in same direction or opposite direction, is going to let you know whether it is in high resistance state or low resistance state. And accordingly, you'll find out whether a 1 or 0 has been stored onto it. And always you'll try to keep the two resistances as far as possible from each other. And that is how your GMR ratio can be increased. So normally you'll try to keep the GMR ratio around 10%. So this is what you will see with your GMRs. It goes only up to 10%. So the difference between the two resistances are not that enough. But then the GMRs actually laid the foundation for MTJs, magnetic tunnel junctions. Now this magnetic tunnel junction, which you're seeing over here, is the wonder device that actually laid down the foundations for your next generation memories. So what you see over here is you have a free layer again and a fixed layer. So two layers you can see very well. And depending on what direction of the upper layer is, you'll have two states, either anti-parallel or parallel. And accordingly, the two resistance states, RAP and RP. And the difference in these two resistances should be high enough that decides your TMR, tunnel magneto resistance ratio. So this ratio as on date has been something around 500%. So people have gone up to that high difference in resistance so that you are able to clearly distinguish between 0 and 1. And of course, you can change the state from anti-parallel to parallel depending on what current you are applying. So if you apply a current from bottom to top, right, so this is the two-terminal device that you have. And if you apply some current from bottom to top, and if that current is greater than your ILH1, so what you're going to do is you're going to write 1 onto it. You're going to change the state of this free layer. And that would be an operation which is called as spin transfer torque. And accordingly, you can actually change the state from parallel to anti-parallel if you apply a current which is going from top to bottom. Please notice this is opposite direction to what you had applied earlier. And if this current is greater than your IHLO, you're actually going to switch to a low resistance state, that is parallel one. And this is what has been shown here. So you can, of course, switch from RAP to RP or RP to RAP, depending on what current you are applying and what direction you're applying. Depending on how large the current you are going to apply. So this is where the two threshold voltages have been shown. So as you keep on applying the current in opposite direction, which is greater than ILH1, you are going to switch from RP to RAP or from RAP to RP state. So this is how your magnetic tunnel junctions work. Now the MTJs have also evolved with time. So you have many variants. So the two important variants are your in-plane magnetic anisotropy, where you have this magnetic anisotropy in plane, or it is in perpendicular form. This is what you are seeing. So this structure has been more popular, reason being that you can scale it down up to like 10 nanometer technology node. You can scale it down up to that. And that is why it can fit very well into some of the modern memories, some of the upcoming memories that you want to have. Now, your STT-RAM is, of course, a possible solution as a universal memory. Reason being that it is non-volatile as flash. It has read or write speed comparable to SRAM. It has a density similar to what you have with your DRAM. It has unlimited endurance, highly scalable, low power consumption, and the best thing about it is that it can have multi-level cell capability. I mean, if you can place these MTJs either in series or parallel, you can have large storages done. In fact, you can use a single transistor to store 3 bits. So some of our candidates, some of our students have already demonstrated that how you can store up to 3 bits. And now they're looking forward for quadruplet, 4 bits. Not only using MTJs, but some of the upcoming devices such as your VCMAs, voltage controlled magnetic anisotropy, MTJs, or SOTs. And other best thing about it is this STT-MRAM uses just same CMOS technology that we are using currently for DRAM and SRAM, with just 2 or 3 additional masks and a cost addition of less than 3%. So all these scenarios actually pave a really good way to use these STT-MRAMs for future technology nodes. So this actually diagram shows the parallelizing STT mechanism or anti-parallelizing STT mechanism. So what you can see over here is when you apply these electrons from bottom to top, and if their orientation are same to the bottom one, what will happen? It will go straight away from this side and it will enter into the region of your other side. Now what happens is these electrons will start applying torque onto it. And this will keep on applying the torque till the time it switches its movement. So the switching of this event is going to change the anti-parallel state to a parallel state. And this is what you're transferring the torque. So this is why it is called a spin transfer torque, because you're transferring the spin torque onto the next side. And once it is changed, you have actually written a 0 onto it. Similarly, you can carry on the other side process also, wherein you have anti-parallelizing STT mechanism, wherein if you apply the electrons from the top, these electrons which are oriented in same direction will actually go off straight away. But the one who are in the opposite direction would get reflected from the interface of the bottom one and will apply torque onto this. And if you keep on applying the torque for a long time, or if you have a huge flow of electrons, I mean, a strong current, if it is there, the changeovers would be quick for large current. But if the current is small, the changeovers would be quite slow. So that way you can control the switching speed. So this switching speed has to be as low as possible. So you'll always try to keep this current as high as possible so that you're having this speed comparative to what you have with your level 3 or level 2 caches. But if you have large current to flow, what will happen is, if the current is large enough, the power dissipation will also go up. So you have to make a balance between all these scenarios. So what this slide shows is a magnetoresistive RAM, which was introduced earlier, where this is where you have your MTJ, and you have a driver on the bottom. That is a planar transistor. Now this planar transistor is going to inject a current through these MTJs. And how would you switch? That switching would be done by some external magnetic field that would be generated by the current that you're applying through this BL line. So this external field that you're seeing is going to actually change the free layer, right? The current that is passing through this. So this free layer would be changed, its orientation would be changed by some external magnetic field. This is what is your conventional MRAM. But as on date, with your MTJs coming as a storage class device, what you can do is you can avoid external magnetic field, and in fact you can use the current that you're passing through this MTJ to switch over the free layer. And the current itself would be quite small. It won't be that large. The key advantages over your conventional MRAM, if you see, is that it has excellent write selectivity. It has high scalability, low power consumption, and you have simpler and faster operations that you can do with respect to what you see with your SRAMs. So those who are done with SRAMs, they can very well understand how quick and simple process this is to change over the state from 1 to 0 or 0 to 1. So the same STT-MRAM cell operation has been shown here in form of your schematics, where you can change over the state from your anti-parallel to parallel ones while applying the current from top to bottom, or from parallel to anti-parallel by applying the current from bottom to top. When you come to read mechanism, it is it is similar to what you do with your other SRAMs and DRAMs as well. So you have conventional read schematic in this form, wherein this is your MTJ, which is changing its state from RP to RAP or RAP to RP. So the two states would be there. And what you need to do is you need to compare with the reference resistance. And that resistance would be sitting exactly in between your RP and RAP. Now, this resistance, which is exactly in between your RP and RAP, is going to give you some reference voltage when you pass similar current through these two branches. So you have a reference voltage over here, and once you have a smaller resistance that is RP or a larger resistance which is RAP, you'll have a voltage which is higher or lower than your V reference. So once these two voltages are compared, you can have either 1 or 0 out of the sense amplifier, which is going to let you know whether 1 or 0 has been stored onto this MTJ. So read mechanism is also quite simple and quite fast, which is not going to consume much power. So this footprint area of your STT-MRAM was given by Grandis Corporation in 2010, where they could achieve a minimum size of 6F square, wherein you can see the MTJ sitting on the top and the drivers on the bottom. So these are the drivers, and then the planar transistors, and the minimum size that you could have achieved was 6F square. So what we tried to do is we tried to reduce the overall size. And that could be done quite easily using a GAA instead of your conventional planar transistor. So with GAA gate allowed, which is shown here, the same has been used here in the circuit completely. So you have a GAA here, and sitting onto it is your MTJ on top of this. So this MTJ can be switched by the driving current that you derive from this GAA. Now, one of the best things that we achieved with this GAA driving this MTJ was that we were able to reduce the size of the cell from 6F square to 4F square. So 1/3 reduction in the size meant a huge amount of area to be available. And that area could again be used for larger storages. So this is what we achieved without compromising anything in terms of performance. In fact, the GAA that we were using for a smaller area could give us larger current in comparison to what we were getting from a planar transistor. So that way we were able to switch this MTJ quickly in comparison to what we were doing with your planar transistor. So this is how actually the overall performance and the area was reduced using GAA. Still, you can see the MTJ is still very small in comparison to your transistors that you're using. So the footprint area can be further reduced if you keep on coming up with some better transistors. So when you come to STT-MRAMs, it's very important that you understand the device level and circuit level parameters properly. And the device level parameters, if you see, they are quite different in comparison to what you do with your SRAMs and DRAMs, the conventional SRAMs and DRAMs. The terminologies are quite different, such as anisotropy and related constant, parameters, thermal stability factors. Then you have your resistance area product, critical switching current, and the TMR that we have discussed. Apart from this, the circuit level parameters are also quite different. So instead of signal to noise ratio and other things, we use write error rates, read disturb rates, sensing errors. And if you see the temperature voltage dependence, which is quite critical in any of these designs, you can see it very well over here that if the temperature of the whole system goes up from 25 degree to 85 degrees centigrade, the TMR suddenly, you can see it goes from this to a smaller one. And that is where you're not able to figure out really the difference between 1 and 0 quite clearly. So you'll always try to keep this TMR as large as possible, but that would be possible with smaller temperatures. And that is why what we had seen in history, that your GMRs used to operate at millikelvin temperatures, very small temperature. Whereas with better materials and better designs, as on date, we can achieve a good performance using MTJs at even 60 or 70 degree temperature. 70 degree or 60 degrees Celsius, we are able to still achieve really good performance, much above your room temperature. So STT-MRAM arrays have also come up recently with these kind of arrays, which was given by Spintech in 2015, a France-based company. And as on date, if you see the market perspective, it's a huge perspective that you see. Most of the companies, top-run companies, have jumped into this business. Let it be Intel, IBM, Everspin, Qualcomm. So all these companies are there into this business. And I was discussing with one of the vice presidents of Everspin. They claim that they have already replaced DRAM by these MRAMs in most of the data centers. And they're producing it in mass and shipping it to different companies based on their requirements. So this is how the memory capacity is also increasing day by day, year by year, by all of the companies. Right? Other than this, what we see is there are different challenges also which are associated with these kind of memories, such as your critical current density. Your MTJ models have to evolve well so that they can be used in different EDA tools. You need to take into consideration different PVT variations, your read speed, reference generation, and of course, the fabrication of PMTJ devices below 50 nanometer technology node. So all these challenges have to be looked after, but then you have huge prospects of STT-MRAM. So this is my last slide for the presentation. So as of now, you have huge prospects in terms of your STT-MRAM, which is a strong contender for the instant-on, high-speed, portable devices with extended battery life. You have STT-MRAM has a huge potential market as a universal scalable memory. And of course, it can replace your ESRAM or eFlash beyond 32 nanometer. And that is what has been done also with DRAMs and other kind of memories. And with time, your NAND flash will also go off. And you know, it's throughout world, most of the developed countries and developing countries have put a lot of efforts in development of all these STT-MRAMs. And as of now, the memory industry is focused on substitution of on-chip SRAMs in next 5 years. And if you talk about MTJs, you need to achieve low MTJ write current. That is what actually has been done also. And now the focus is on chip distributions and yield. And of course, you have to come up with perpendicular MTJ-based STT-MRAM that is scalable up to 10 nanometer technology. So huge prospects with this STT-MRAM, and they're going like anything. So not only memories, they have huge applications in neuromorphic computing, in logics, and also quantum computing. So Spintronics is one field which is rapidly developing, and I think there is a huge career in this area which people can look into. So with this, I would like to stop, and I would be happy to answer some of the queries from the audience. Yeah, so there is one question: how altering of spin direction is being done? Yeah, that is being done in both direction. So you have to either. So what you need to do is, if I come back to this slide, you have a contact on the top, and that is your BL line, right? So BL line, which is there, the bit line, which is going to be reversed, which is either going to be 1 or 0. And accordingly, you're going to shift the direction of the current. And that will be need-based. So the current CMOS technology is all based on silicon. They're not magnetic materials. They're not ferromagnet. So that is why the spinning is not possible in current CMOS, right? So you need to change the material also. It's not that only the H and E fields will generate the magnetic field and then the same material can be used for different purposes. You need to change the material also.
One student is asking principle of physics of Spintronics. Principal physics of Spintronics.
Yeah, so it's all based on your spin of electrons. I think you can study those things right from the beginning, right from the class 12th, where you have all spin of electrons available. So every material has its own spin. Right?
Okay, thank you, sir. One more last question, sir. How the
Yeah.
yield of chip distribution can be increased?
For Spintronics or something else, or in general?
In general,
I think, yeah. So in general, if you want to increase the yield, there are n number of ways by which you can increase. So if you keep on putting up more and more transistors, more and more pins, of course the yield will go down. And to increase the yield, you have to follow different number of ways for interconnects, for transistors, right? So your pins, your crossovers, all those things have to be looked after. So it's a complete area of research that you're asking about increase in yield. So as far as Spintronics is concerned, people have already come up to a stage where now they're looking for increasing the yield based on conventional techniques.
Okay, thank you very much, sir, for accepting our invitation and giving an introductory talk on the Spintronics on our 5-day workshop. So on behalf of organizing committee, I thank you, sir. Thank you, Professor
Thank you
Brajesh.
very much. Thank you. Thank
It
you
is
very
a very
much.
nice session, and definitely the participant will get benefit from this.
Right,
Now,
my pleasure. My pleasure.
yeah.
Thank you very much, and bye all of you.
Okay, thank you. Participants, we'll break here for 10 minutes. Okay, so 4:20 is there. We'll again start at 4:30. Introduction about the TCAD tools. Okay, so stay connected, please.